All right, so quick recap. We're talking about stable versus unstable environments. Remember we were talking about the idea with the bowl. In an unstable environment, regardless of where we put our little air bubble or air parcel, it's going to do what? Fall off the bowl. In what direction we don't know, but it's going to go somewhere. In a stable environment, the bowl is flipped around, meaning that we have our little air pocket, our little bubble is going to start at a certain position, and regardless of where we move it, if we put it on this side of the bowl, we put it on that side of the bowl, this side, doesn't matter. It's always going to return down to its original spot. Okay? So stable versus unstable environment. All right. Now how does that work in terms of weather patterns? Well, we were talking about raising air parcels. So to create an unstable environment, what you've got in particular at times is your air parcel, right, our little pocket of air, is warmer than the environment. So if it's running at 85 degrees and the outside air is 75 degrees, then this is warmer. And we already know the concept of warm air rises, right? So if this is 10 degrees warmer, it's going to continue to rise until it cools to the point that it is stable with the outside air. It's that concept that the Earth is always trying to balance itself out. But we also know that if our little air bubble closer to the surface, and if we know it's closer to the ground, it's going to have more impact to gravity, thus it's going to be a tighter package. There's going to be more kinetic energy, which is why it's warmer than the environment, right? Because all the molecules are smashing into each other, so they're creating more energy. Well, just like a balloon, once that starts to go up into the atmosphere, and you know from when we go up in the atmosphere what happens to pressure. It starts to decrease, right? So if it starts to decrease, our balloon, our little air parcel starts to expand. As that starts to expand, that's going to decrease the amount of potential for these molecules to kind of smash into each other. Thus, it's going to cool the temperature. All right? So in an unstable environment, a couple of rules to remember. Our little air pocket is warmer than its surrounding spot, so it's going to rise. It'll expand. It eventually cools, and we'll get into what it means by adiabatic cooling. And it keeps rising as long as they're warmer than the environment. So until it finds that point where it hits the same temperature, that's going to continue to rise. And it creates what's called an unstable environment. Meaning that you're going to continually create movement in the atmosphere until it hits that level. Okay? That's why thunderstorms can get to grow to 45, 55, 65, 70, 70, that's a little much. But 45, 50,000 feet up in the sky. That's how high some of these clouds can get, because they're trying to find that temperature. And once you get up into that high in the sky, obviously the temperature is a lot colder, and so that air is just going to continue to rise, which just cools it and creates a bigger and bigger and bigger cloud, which is sort of how it works. Okay, so that's an unstable environment. And then in a stable environment, the opposite happens. Think of the bowl again. If we start with an air parcel way up here in the sky, but it's cooler than the surrounding environment, it's thus more dense. If something's more dense, and has more density, if something's cooler, it's more dense, has more density, so it's going to sink. And so our air parcel is here. We're in a very hot environment, so it is going to start to fall because it is heavier. Okay? Now, as it falls, we know just the rules of gravity itself. If something falls, gravity is going to have a bigger effect on it. Pressure is going to be stronger. And so this balloon, or this air parcel that is very big now, starts to condense and shrink. Well, if it condenses and shrinks, it compresses. When it compresses, what happens to all the molecules that have all this space? They now have less space, and so they start to bang into each other, which creates more friction, energy, kinetic energy, and so it starts to warm up that air pocket. And so that air pocket eventually becomes the same temperature as the environment. So the idea here is that it sinks, compresses, starts to warm up, keeps sinking as long as it's colder in the environment, and it turns into a stable environment. So think of it in terms of like if you had rocks in your hand and you throw them up in the air. Okay, so you're creating a force, throwing these rocks up in the air. Well, if you're in a stable environment, those rocks will, it doesn't matter how high you chuck that thing in the air, it will sink back down to the ground. Okay? Versus if you have, let's say rocks that are made of helium, for example. We'll just make it up, because why not? It's a Monday morning, we can do that. So if I got a rock with a helium in it, and no matter how much I try to push that rock down, it will continue to rise. Kind of like, have you ever seen, if you had a, if you've been in the pool or even out in the ocean and you had a like a beach ball or something like that, try to hold it under the water, what happens? Yeah, it's going to pop right back up, right? Because the air inside of that beach ball is lighter than the dense water. And so just physics says that has to sit on top, which is why for the most part we don't sink, right? We kind of sink, but we don't really sink. It's because one, we're sort of filled with water and a sodium solution, and salt that actually sits up top of water as well. It's less dense, and so that's why we naturally kind of float. All right, everybody got that? All right, perfect. So now we're going to talk about lapse rates. Why do we need to know about lapse rates? Well, they're kind of important. Lapse rates are the warming or cooling of the air parcels as they either go up or down in the atmosphere. Okay? So the idea of the lapse rate, it's a change in temperature versus change in temperature per change in height. Okay? So if you look at the lapse rate, it's basically this: delta T over delta Z. Delta means change, if you haven't taken chemistry or if you're a little rough on that. So it's basically, what's the change in temperature over height? Does your temperature go up? Does your temperature go down? Very simple. And there's two different types. There's a dry lapse rate and a wet lapse rate, or what we call the moist lapse rate. We're not going to use the word moist because it's a terrible word. I get yelled at when I use it on TV. So we'll say wet. Okay? So the lapse rate is basically at what height or at what temperature are you going to either warm or cool as you go up or down in the atmosphere. So if I'm a little air parcel, I'm a little bubble of air, what is the change in my temperature when I'm going up in the air? And what is the change in my temperature when I'm sinking through the air? Okay? So that's our lapse rate of what we're going to be looking at. Now, we're going to get into some squiggly lines here, so just stay with me. All right. So the first one, a dry adiabatic lapse rate, which is DALR, you can just notice that. It's used for unsaturated parcels. Okay? It's a very easy number. For every 1,000 meters we go up in the air, cool 10 degrees. Perfect. I like easy numbers, right? So if we're at the surface, we go up 1,000 meters. Let's say our starting temperature is 90. We go up 1,000 meters. That temperature is now 80 degrees. Pretty simple, right? 70, 60, 50, 40. There you go. Now, here's the problem to that. This is in an unsaturated environment. Do we live in an unsaturated environment? No, we do not. So obviously, this is going to be invalid, right? Can't use this. Now you say, well, why did I even just put it in my notes? Well, we use it because this is sort of this standard, or sort of the baseline that we use for saturated parcels. Okay? So we got to have an idea of where we need a baseline, where we start, and then we go from there. And that's where we use the wet lapse rate. Okay? And here's the trick to this one. Whereas the dry lapse rate is basically every 1,000 meters you go up or down, you change your temperature 10 degrees. Psh, very simple. This one here, notice, very important part right here. The value is variable depending on the amount of water vapor that you have in that air, which makes sense, doesn't it? Like a drier air mass is probably going to follow closer to the dry rate, right? It's going to be more on the 8, 9 degrees per 1,000 meters. Whereas if you have more water vapor in that air pocket, it's going to take longer for it to change temperature, right? Why is that? Why do we know? Think back to your exam. what do we talk about with water? Latent heat. Because water is more dense, what do we need more of in order to make changes to it? Energy, right, very good. Right? So we've got to pump more energy into something that has water in it because water is super stingy and it takes a while for it to make a change. That's why we're talking about latent heat, making those phase changes. It takes a while because it's just stingy. It's very dense. It doesn't conduct heat very well, so we got to pump a lot into it. So on average, our lapse rate is right about 6 degrees Celsius per 1,000 meters, or about 3 degrees Fahrenheit per 1,000 feet. Okay? So clearly you notice that it's lower than the dry adiabatic lapse rate. And it'll never be greater. It'll always be less because we have that water vapor in there. Okay? So what does all this mean? You're like, all right, I got all that. What do I care about it? All right. So the idea here is that cooling, when you lift something up into the sky, that cooling produces condensation. Okay? So the cooling process produces condensation. Well, if we get enough condensation together, it forms a what? One of those guys. Forms a cloud. Okay? Now the condensation also releases latent energy, which we know latent energy is related to water. Because that's how we either get water to change from one phase to another. So evaporation cools and condensation warms. All right? Let me explain that real quick. So if I'm taking air and we're throwing it up into the sky, it's cooling. So if I'm going to take something that's in a water vapor form, just like it is here in the room, right? We can't see it, water vapor. It's in this room, but we can't see it. But if we continue to condense it, and we throw it up into the sky and it cools and cools and cools, down to the dew point, very good, right, down to the dew point, we start to create condensation. Well, in order for it to go from that gas to a liquid state change, we have to take an enormous amount of heat away from that water vapor, right? So we're cooling that process. So meaning that we're adding heat here, and we're taking away heat from in here. Okay? So that's a cooling process. Now, what's the converse of that? If we are taking this air and we're condensing it, right? We're pushing it down closer to the surface, and so it's getting tighter and tighter and tighter. So the molecules are all smashing into each other, so we're creating more energy. We are drying the air mass out. Okay? So we go from a cloud to no cloud. But what we're doing here is we're increasing, let's use our little parcel. So we're increasing the amount of energy inside and decreasing the amount of energy outside. So we're either adding to or taking away is the bottom line. So if we're adding energy to this, we're obviously warming it up, right? So this in fact would be warmer. That would be cooler. Which makes sense, doesn't it? The closer you are to the ground, the warmer you're going to be. The further away from the ground you are, the cooler you're going to be. Bada bing. Okay. Is that good? Yeah? All right. Okay. So why do we care about all that? Well, because in order to figure out what kind of environment you have out there, you have to figure out what are you looking at? Are you looking at clouds? Are you looking at dry skies? Are you looking at sunshine? What are you going to see out there? And so one of the first things you have to look for is you look for when do clouds start to build, okay? And they all have this particular area called an LCL. This is a lifting condensation level. So this, if you want to think of it, is basically where the cloud forms. At what height in the sky do you start to see clouds forming? Today I think that may be a little difficult because we're fairly overcast. building. Oh yeah, we got hot garbage mess up there, so that's not going to. All right, but if we had a day, let's say a typical summer day, where we start off sunny skies in the morning, and then as we get into the afternoon, you start to see those clouds build, right? So if that's the case, then you know that if you look out there, and if we ever get one of those days again, when we get one of those days again, let me have something dramatic here, that go out and look, and you'll notice that each and every one of the clouds that you see, the bases all pretty much start at the exact same level, okay? That's your LCL, that's your lifting condensation level. So air beneath that is too dry to condense until you get to that point. Bam, as soon as you get to that point, that's where your condensation level starts, and that's where you start to build your clouds. And so when that happens, that's when all of this lapse rate process takes over, okay? So the point is that you're dry, wham. I hit a point where I start to condense. Now I'm using that wet lapse rate. And then for every however much water vapor I've got, that will determine how fast that air cools, okay? So that's the base height for the clouds. So it's just like this. So if our dew point is 5 degrees, okay, we start off at the ground, we're at 25 degrees, way warmer. So we're not going to have any cloud, right? We haven't hit condensation level. So let's say if we rise 1,000 meters, which we know, what's our dry lapse rate? 10 degrees, 1,000 meters, simple math. Boom, we're now down to 15, okay? Still warmer than the 5, so we haven't turned into a cloud yet. So we've got to continue to cool. So we go up another 1,000 meters. We drop from 15. Remember, our dry lapse rate is 10 degrees per 1,000. So drop it 10 more. Now we've hit 5. Looky, looky. That's our dew point. So we've now reached the level of saturation. There's our cloud. Boom. So our LCL starts at 2,000 meters. So anything after this is all going to have to change, right? Because we're no longer dry. So that's why when you say before, you say, well, why do we even need to know this dry lapse rate thing if all air is saturated? Because the way the physics of meteorology work is in order to be able to create or understand where your clouds start, you have to be able to create some uniform system so that you can go up into the sky. So as soon as you hit this point where your air temperature is the same as your dew point, which is basically when you start to create a cloud, then you switch. And instead of going from 10 meters or 10 degrees per 1,000 meters, you go over to that wet lapse rate. And that's the one that's variable. It all depends on how much moisture you got. It could be 6 degrees per 1,000. It can be 4. It can be 7. It can be 3, 8. Doesn't matter. It all depends on the amount of moisture that you have. So that's how the two work in tandem. Okay. So now the third one we put into this is called the environmental lapse rate, because obviously we've got to be able to use our air. Well, our air parcel isn't like in a bubble, right? That sounded kind of funny because it actually is a bubble. It is not in a bubble. It is in the environment. And so the environment itself is going to have a certain amount of moisture to it, right? So if the environment's got a certain amount of moisture to it, then we've got to figure out, is our air parcel warmer or cooler than that, okay? So it'd be nice if it was just one number, like a 10 degrees per 1,000 meters, but unfortunately it is not. So it continually changes. And one of the reasons why we know it continually changes is because we measure it twice a day with weather balloons that have these little, they're almost like little milk cartons, and they're called radio zones, okay? Same thing that the hurricane hunters, you know, when they talk on Weather Channel about the hurricane hunters flying into the planes, and how they get all that info in there, is they drop these little radio zones in the center of the storm, and they measure everything from temperature, barometric pressure, wind speed, wind direction, moisture content, all of that. And then all of that's fed back so that the computer models that show you where that storm is going have information so that they can try to figure that out. Now the crazy part is that these weather balloons are literally balloons. And you'd say, well, couldn't we come up with a better system for that now? Not really. We haven't thought of one yet. So twice a day, 6 a.m., 6 p.m., the weather stations that are all across the country. Right here. So every single one of these stations at the exact same time will go out, literally go outside with a weather balloon and launch it in the sky. And so then all the information starts to come in. And that's how we sort of create this spider web network of weather info that goes into all these forecasts. In fact, I think I've got, let's see if I got some, pretty sure I have some pictures of it. Well, thought I did. Okay. So the way this works between the two is when you look at lapse rates, you have to figure out where is your air parcel. Is your air warmer or colder than the air surrounding it? Basically the environment, right? So the dry lapse rate, which we know is the standard, it's the set number, 10 degrees per 1,000 meters, is going to be a very set line, just like that. Our environmental lapse rate is going to be somewhere between where the dry is and where the wet is, okay? And so what we try to figure out is our wet lapse rate is based on the moisture content of the air itself, right? And so where do these two interact? And that'll let us know, do we have a stable or an unstable environment? I'll explain how this works. Okay. So for a stable, or to understand stability, we compare the parcel temperature, our little air bubble, to what the environment temperature is. So there's three ways to look at this. There's absolute stability, there's absolutely unstable, and a conditionally unstable environment. It can be one of the three, right? Now, an absolute stable environment is just like the bowl, like we remembered before. Regardless of where we put our little air parcel, our little marble, it's always going to go back to the original spot, right? An absolute unstable environment is going to do the exact opposite. Regardless of where we put this, it's going to fall somewhere, okay? And then sort of a conditionally unstable environment, that's all going to be dependent on what's happening in the environment surrounding it. Well, the bottom line, what we're going to be dealing with here in the class is that we don't really deal with either purely stable or unstable environments, right? We deal in the messy, which is sort of our conditionally unstable. Because think about it. If we had a purely stable environment, would we ever see any clouds? Probably not, right? Because the air couldn't rise. Any air that, think of the rock example again. Any rocks that we try to throw up in the air would do what? Immediately come back to the ground. So any air that we try to chuck up into the air, chuck up in the air, we can't form it in any clouds. Just goes right back to the surface. That'd be pretty boring. One, we'd roast to death, right? Because we wouldn't get any rain. And two, I'd be out of a job. So we can't have that. My children got to go to college. So now, converse that, if we had a purely unstable environment, what would happen? What do you think? Like if the air mass just continually rose and rose and rose and rose and rose. What do you think? What happens if we get air moving up and we create lots of clouds and thunderstorms and that?
We would drown.
What?
We would drown.
Yeah, we'd be dead, right? We'd be like in, Jupiter, Venus, I don't know, something like that. It would be a very hostile environment, and none of us would really enjoy it that much, right? And we'd probably be pretty soaked. So clearly neither of those happen. So the world sits in a conditionally unstable environment, and it's all based on what's happening around with the environment itself. All right. So here's the idea. And I'll just go through these real quick, and the conditionally stable one is the one we want to talk about. I just want you to visually see this. I'm a visual guy, I got to see this stuff. So in this example of an absolutely stable environment, our air parcel here is going to continue to fall because it is always colder than the environment surrounding it. So it doesn't matter how much of this we try to throw up into the air, it keeps falling back to the surface. This is the example of we would literally have no clouds and probably very little weather. And everything would sort of croak and die. Okay? No good. Parcel won't rise. So in an absolutely unstable environment, the exact opposite is true. Regardless of how much we try to press that air down and compress it and dry it out, it will eventually continue to rise, right? So if we have it here, our air temperature is 25 degrees Celsius, dew point's 15. We already know that's an imbalance, right? So we got no clouds. So if this is warmer, what does warm air do?
Well,
Right, starts to rise. So it's going to rise. It hits, oh looky, temperature and dew point are the same. There's our LCL, right? Our level of condensation. There's our cloud base. And so that just continues to rise. And so the problem is that generally these start to balance out. Once that air temperature and the dew point become the same, you have a cloud, but notice that it's still warmer than the surrounding environment. It's minus 11 degrees Celsius. That's 3 degrees, that's warmer. So it's going to continue to rise. If that's the case, we've got a horrible environment. Showers, thunderstorms, cats and dogs falling from the sky. Biblical stuff, man. We don't want that. We're not ready for the reckoning just yet. All right, so what do we live in? We live in a conditionally stable, unstable environment. At times, our air parcel is warmer than the environment, so it starts to rise. As it rises, it cools, creates clouds, gets to the point where temperature inside the air parcel of the cloud itself becomes similar, if not the same, as the temperature outside. Once it does, it stabilizes. And if this temperature outside starts to warm, this becomes too cold, what is this going to do? If it's colder, it's more dense, it's going to start to sink, right? So what you have is you have this environment. We have air continually rising. Actually, I did this the other way here. You have air continually rising and falling. And so throughout this environment, you're either creating an unstable environment or you're creating a stable environment. And so this just kind of flip-flops throughout the day, throughout the week, throughout the month, throughout the years. And that's what weather patterns are. Weather patterns are either conditionally unstable, meaning that they're rising, or they're conditionally stable, meaning that they're falling. There's no absolutes to it. So if there was, there wouldn't be much weather. That's why weather all deals in conditionals, depending on the environment itself. Okay. All right, so what are some of the lifting mechanisms that we deal with? There's a couple of different ones in particular. We already know about what convection is, right? If you heat something up, it starts to rise. Once it gets to a point where it cools, it starts to fall, right? Little convective oven, just like that. Convergence is just what it sounds like. Two things kind of converging together, or slamming into each other. Orographic lifting is mountains. If you've ever been out, or if you've seen pictures of mountains out west, do you ever notice sometimes they've got little clouds right on top of them? That's an example of air hitting the mountain. It moves up, so it's forcing its way up, and of course it cools to the point where it condenses. There's our cloud. And then of course we've got frontal lifting as well, and that's from warm and cold fronts. So let me show you what it looks like. All right, so the four lifting mechanisms are basically this. Convergence. We know if we've got an area below pressure right in the center, we know that the air mass is moving in. So if it's moving in towards the center of that low, what's part of the problem? We got too much there. We got to do something with it. So of course, it moves up. And if it moves up, it eventually starts to turn into a cloud. So that's convergence. Convectional heating is just what we're talking about, just like an oven. You've got wind moving up, air moving up, cools. As it cools, it starts to fall. Bless you. And so you get this creation of this little convective circle or cycle. Okay? All kind of moving throughout. Orographic lifting. There's our mountain. So the air moves, and as it slams into the mountain, it gets forced up. And as it gets forced up, it starts to cool, right? Because obviously the top of the mountain is going to be colder than the bottom of the mountain. Makes sense. So as it cools, what do we know from our lapse rate? It cools to a certain point where it becomes condensed. And it's saturated. If it's saturated, it creates a cloud, right? So if it creates a cloud, this is what we'll get. We'll get little clouds, generally on the windward side, which is the side the wind is coming from on a mountain. And then our last lifting mechanism is by a front itself. Now, a cold front, because it's stronger, has a stronger push of cold air, and it sort of forces the warm air up very violently, which is why you can get big thunderstorms on cold fronts, because that cold air is so dense, it's pushing down and it's forcing all of that warm air up. And as it pushes that warm air up, you can really get clouds to start to build. So those are our basic 4 lifting mechanisms that we use, and each of these mechanisms follow that lapse rate formula, so to speak. So if the air's dry, it's going to lift at a very uniform level, 10 degrees per 1,000 meters. But once you start to get it to the point where it condenses, and we've turned it into clouds, at that point, well, then it's all based on how much moisture we have. If we have a lot, if we have a little, that will change the amount of lifting based on how much moisture we've got. So here's an interesting thing. We're talking about orographic lift. So orographic lift is basically the mountain lift. And so the windward side, or the side that the wind is coming in from, is generally really cool, cloudy, lots of vegetation, lots of precipitation. And the leeward side, which is the other side of the mountain, usually is fairly dry. It can be sometimes what's called a rain shadow desert. The Pacific Northwest is a great example of that. Okay? Let me show you some stuff here. Trip check. Okay. So, in Oregon, they have all of these cameras set up across the they have all these cameras set up across the state that give you an idea of what the weather conditions are, so you can get a so you get an idea of what you're looking at. So let me find a GEOL. There we go. Okay, so this is a perfect example. This is a live shot from about 7 minutes ago. This is on I-5, which is right outside of Portland. So you notice, got a lot of trees, right? Typically like what you say, oh yeah, that's what Oregon should look like. Correct. Let's go. Okay, so that's kind of what it looks like, right? Lots of Douglas fir trees, Looks like Oregon. Okay? Now, if we go into southeastern Oregon, that's what it looks like. A little different, huh? Kind of looks like what? West Texas, doesn't it?
Mhm.
Yeah. Because Oregon is split up. Yeah, there's Basque Station. This is in southeast Oregon, just north of the Nevada border. You know what's out there? Right, nothing. Absolutely squat. There are counties out there that are literally about 4,000 miles apart. Like one county is about 4,000 miles. They've got one sheriff, and if you live out there, which many people don't, but if you do live out there, you'll see the sheriff may come every third week. Right? The only thing that are out there are these big ranches and a bunch of kind of weird polygamy cults, which nobody really, I swear, they're out there, but nobody really messes with them. Because this out here, northern Nevada and southeast Oregon is pretty much like the Wild West. It's sort of, don't go on someone's land. They may give you a warning shot once, and then they're going after you. So, but I mean, this is what it looks like, right? You look at this and you say, that's not Oregon. Oregon's supposed to be like trees and hippies and stuff, right? This looks like what? That looks like between Fort Stockton and El Paso. I drove that. That's what it looks like, you know, without the mountains, obviously. So that's an example of a range shadow. This is a high desert plateau. Look at the elevation. Almost 4,500 feet, right? So it's just under a mile up. But you'd say, okay, well, if it's out there in the northwest, why doesn't it have any rain? Where's the vegetation? Nope. What's just what's just west of there? What would cause that not to be there? Right? For orographic lifting, we are hitting a mountain range, right? So the Cascade Mountains run all the way down the spine of Oregon. And so the way it looks, let's do shadow light. Shadow light. Listen to me. You can tell it's Monday. I can't talk at all. Okay, here we go. Perfect example. So this is what the state of Oregon looks like. So the mountains are right here. Okay? They got two sets. One here and one here. This is the Coast Range. This is the Cascades. Coast Range generally runs anywhere from about 1,000 to 2,500 feet. It's a very old mountain range. It's been there for millions of years. One of the oldest in the country, or oldest in the world, actually. And it's less than the Cascades. Cascades run anywhere from around 4,000 to about 11,000 feet. It's one of the highest peaks. Okay, so fairly sizable as it moves through. Now, why would this one here, western, closer to the ocean, be less than this one? Why is this one smaller than this one? Right, erosion, exactly. This gets hammered by these big storms that come slamming in each and every year for thousands and thousands and millions of years. And so it's eroded that down. The Cascades are relatively newer mountains. The Rockies are a fairly new mountain range. You think, well, they've always been there. Not really. They haven't always been there. Yeah.
Yeah, I was reading something about like the Grand Canyon actually used to have like it was a massive like mountain range.
Yeah.
Because at the bottom they found just rocks that had to be
Yep.
or things that were compressed, I guess.
Yeah.
It's crazy.
Yeah. Yeah. Grand Canyon used to be a lot bigger than it was, and it's just eroded away over the years. The Moab Desert out in Utah is the same way. You know, I mean, these things have been around for hundreds of millions of years. You know, one of the oldest mountain ranges on the planet is the Appalachians over in the eastern U.S. It's about 200 to 300 million years old. Used to be massive. That's why they don't see the same fossils on the east versus the west side of the Appalachians, because the animals just couldn't get over the mountains, right? So they had two entirely different species. But that's when they started finding them, and they kept thinking, well, how in the world is this possible? Because these mountains aren't this big. And so they thought, okay, well, these clearly must have been a lot bigger way back in the day. And it's just they've been eroded over the years. And it's just one of the oldest mountain ranges, which is why they're so sloped now versus, these more rocky ones, or even like the Grand Tetons, which are over here in towards Wyoming and Idaho as you work your way south. But anyway, so the idea is that you've got all of these storms coming in off of the Pacific, and so you have all of your vegetation and your precipitation out on the western side of Oregon, right? And then what happens? All of that precip, all of that rain, all of those storms try to move up and over the mountains. Well, once they get up to the top of the mountain, sure, they can produce some pretty good snow, which is why the Cascades are really snowing. They've got all these ski resorts up there. But then what happens? As that air moves down the mountain, what do we know from our lapse rate? If we're taking our air parcel here and we're compressing it, what are we doing? We're warming it up, right? If we're warming it up, we're probably doing what to the moisture in that air? It's drying out, right? So that's why this is what's called a rain shadow. Most big mountainous states, Colorado, Wyoming, Utah, Oregon, Washington, they all have these entire areas of the state which are basically just high plateau deserts, right? That's why the front range of Colorado is just flat like it is.
Yeah, it's incredible how
fast it changes.
Nothing is out there. Once you get past DIA, all from Wyoming to Kansas.
Yeah, nothing, right? And that's why the Central Plains is the Central Plains, and it's why it's windy and it never stops. There's a reason why the old song, Home on the Range, the deer and the antelope play, right? The winds are blowing. There you go. That's why it's so windy. That's why people create, when they're in western Nebraska in particular, and in Kansas and Colorado out on the front range there, if they have ranches, they'll create entire rows of trees, and it's basically a wind fence. So if your house is here, and wind generally comes from west-east, and this is the windward side, you'll plant big trees real close to the side of your house because it moves the wind over.
Like next to the highway.
Yeah.
They'll build those things for the winter to prevent snow. Like it'll be a big problem.
Right, you get big snow drifts through there as well. Yeah, I mean, Western United States living is completely different than anything that we experience here. It is a whole different. That's why some of the folks out west that are used to that, and they come here, they're like, oh, great, a storm, awesome, yeah, we're gonna get some rain today, and you're like, watch out, and then 4 inches later, you're soaked and you can't go because the road's flooded out. Whereas out there, it's just a completely different story. So it's kind of cool, but that produces a different set of problems if you live in, let's say, that picture I showed you from Basque Station. That's basically where it is right there, right? So if you're out here, what do you got to be concerned with? Water conservation, right? What am I going to be able to grow? How are we going to live out there? Because out here, it's totally different than living over on this side of the state. So that's just kind of an example of orographic lifting and how it can really make changes to sort of how you live. Okay, last thing before we go. I want to show you this because this is really kind of a cool visual of how a cold front works. So a cold front, remember at the beginning of the class we talked about a cold front's basically like a cow catcher, right? It's sort of that front edge of the train. And so it pushes through the warmer air, forcing it up. And so this is a really good graphic to get an idea of what that looks like. So that cold air mass is moving in, and obviously it's cold, so it's dense, so it's going to sink closer to the ground. So the closer it gets to the ground, right along the cold front, it abruptly lifts all that warm air. So the more violently you take air, you throw it up. If it's really warm, what do we know? That it's going to be warmer than the environment, so it's going to continue to rise, right? So it's going to continue to rise. Well, if you throw enough of that up into the air, you're going to create these huge big clouds, or what we like to call cumulonimbus clouds, or as you and I like to call them, thunderboomers, right? Which we'll get into next week, I think. So that's where most of our active weather is right along the cold front. Speaking of, take a peek outside right now. Getting a little dark out there, isn't it? See, that's what happens when you do weather for a living. You turn into an idiot and you can't stop. Like, I've been staring at it for 5 minutes now. In the corner of my eye, I keep watching to see how dark that sky's getting. I knew it was coming because I didn't bring my umbrella either, so. I just said that on camera. I shouldn't have said that. I didn't mean it. Anyway, so this is the idea, is that these cold fronts come in, this cold air mass abruptly moves that warm air mass out of the way, and that's where we get our big thunderstorms that start blasting on through. All right? Now, the good thing is that at least for us here, when these cold fronts actually do make it here, guess what? Cold front, cooler air, right? Yay for us. But the problem is that these weaken considerably as they get down this far south. Part of it's just the latitude, part of it is they run into the Gulf of Mexico influence that pretty much dominates most of the weather pattern here. Even in the wintertime when we get those big cold fronts coming through, it's cool for what? A day? 2? And then it starts to moderate out, right? Now obviously last winter we had some extremes where it was cold and we got snow. That was because the cold air was already in place. The only way we're going to get snow here in Houston is we've got to have that cold air here already. Because if we try to move it in, by the time we move it in and then we try to cool it down and make snow, forget it, it's not going to happen. You have to have it there already, and then you got to bring some extra moisture in, and that's how you get snow. Otherwise, not going to happen here. So that's orographic and frontal lifting. And these basically are so this is the basis of kind of what we're going to talk about for the rest of the semester, is how do each of these air masses and these cold fronts moving in, warm fronts moving in, how do they develop into what are called extratropical cyclones, or basically big mid-latitude weather systems, the big thunderstorms that can create not only thunderstorms but tornadoes, flooding, all of that good stuff. And we're getting into the fun part of the class now. We had to get the basis down. You got to understand how everything works, and then we can really kind of crank it up from there. So that's what we're going to deal with. Sound good? All right. Okay. All right. Let's get you out of here before everybody gets wet. We're going to get poured on here.